Assalamu alaikum. Bismillahir Rahmanir Rahim. I welcome you to the 37th lecture for the series of lectures on advanced computer architecture. Today, after a brief review of what we discussed last time, we will be talking about the performance of multiprocessors with symmetric shared memory and distributed shared memory. Then be talking about the synchronization problems in parallel architecture and the solutions for these problems. Then we will conclude our discussion onto the parallel processing today. So far, we have discussed the sharing of caches for multiprocessing in the symmetric shared memory architecture and in the distributed shared memory architecture. While talking about the sharing of caches in these two parallel architectures, we have studied the cache coherence problem in both the symmetric, shared, and distributed architectures. And we have noticed that this problem is basically performance critical. Last time, we studied the cache coherence protocols which use different techniques to track the sharing status and to maintain coherence without performance degrading. Here, we notice that these protocols can be classified as the snooping protocols and directory-based protocols. These protocols are implemented by using finite state machine controller. While talking about the snooping protocols, we notice that the snooping protocols employ write invalidate and write broadcast techniques. Here, in these techniques, the block of memory is kept in one of the three states, that is, the shared state, the exclusive state, and invalid state. In these states, each cache block tracks these states and the controller responds to the read or write request for a block of memory or cached block both from the processor and from the bus. However, we noticed that there are some complications such as the write traces, intervention, and invalidation, and these complications have been observed in the implementation of Snoopy protocols. And to overcome these complications, number of variations in the finite state machine controller have been suggested. We discussed these variations last time, referred to as the MESI protocol, the Berkeley Protocol and Illinois Protocol. These variations basically resulted in slight modification in the finite state machine by introducing an additional state. Here, the MESI has 4 states referred to as the modified state, exclusive state, shared state, and invalid state. Then we talked about the Berkeley Protocol, wherein we found that the 4 states are owned exclusive, owned shared, shared, and invalid. Whereas in case of Illinois Protocol, these 4 states are private dirty, private clean, shared, and invalid. Last time we also discussed that the larger multiprocessor systems employ distributed shared memory. That is, a separate memory is provided with each processor. Here, the cache coherency is achieved by non-cached pages or by using a directory that contains information for every block in the memory. The directory-based protocols, in fact, tracks the states of every block in every cache, and it finds that caches having copies of block being either dirty or clean. Furthermore, similar to the Snoopy protocol, the directory-based protocols are implemented by using finite state machine controller having 3 states. However, the 3 states of the directory-based protocol controller are the shared state, the uncached state, and exclusive state. This can be observed from this state diagram. Here, we notice that these protocols involve 3 processors, or say the nodes, and these nodes are named as the local node, the home node, and the remote node. The local node, in fact, originates the request. The home node stores the memory location of the address, and the remote node holds the copy of a cache block, whether exclusive or shared. We also notice that the transactions in a state machine are caused by the message passing, such as the read miss message, write miss message, invalidate, or data fetch requests. these messages are sent to the directory to cause actions such as update the directory states, and satisfy the request. Whereas the role of the controller is to track all copies of memory block and to indicate an action that updates the sharing set. Now, with this much review of what we discussed last time, we are going to discuss the state transitions and messages generated by the finite state machine controller in each state to implement the directory-based protocol. Here, in order to discuss this, we are going to consider an example distributed shared memory multiprocessor having two processors denoted by the processor P1 and processor P2. Here, each processor has its own cache, it has its own memory, and its own directory. Here, if the required data is not in the cache and it is available in the memory associated with the respective processor. Say, for example, if the processor is P1, then the memory associated with P1. And if we are considering the processor P2, the memory associated with the processor P2 is considered. Then, in this case, the state machine is said to be in uncached state, and the transition from one state to the other state is caused by message passing. These messages may be a read-miss message or a write-miss message, invalidate message, or data fetch request. Here you can see an example table which shows the initial cache states when it is in an uncached state. That is, we assume that the block of data is not in the cache, rather it is available in the memory. And at the first step, when P1 writes a value 10 to the address A1, then in this situation, the following three activities take place. The first activity is the bus action. The bus action is write-miss, and the processor P1 places the address A1 on the bus. The second activity is that the data value reply message is sent to the controller, and the processor P1 is inserted in the directory sharer set. Say the directory sharer set now contains only one element, which is P1. And the third activity is the state transition from uncached to exclusive state. You can see this thing that these three activities are shown on the table. Now let us consider another step, and in this step let us suppose that P1 reads at A1. In this particular case, the CPU read hits occur. Therefore, the finite state machine now stays in the exclusive state. Because this is a hit, therefore no message passing takes place. At the third step, when processor P2 reads from A1, in this particular situation, the read miss occurs on the bus because the processor 2 is initially in uncached state. Therefore, the controller states of processor 1 and processor 2 change from uncached to shared state because it is now have to move into the shared state. The second activity is that the processor 1, being in the exclusive state, remote read write back is asserted and the state changes from exclusive to shared for P1. And a value 10 is read from the shared memory at address A1. This is read into processor 1 and processor 2 caches at A1, and both the processor 1 and processor 2 controllers are inserted in the sharer set. That is, the elements of the set are the names of the processor 1 and processor 2. This is very much clear from the third activity line, which is shown here. Now let us see how the controller works at the fourth step when P2 writes a value 20 to address A2. As we have said in the beginning that the addresses A1 and A2 maps to the same cache block. Therefore, the processor 1 finds a remote write, so the state of the controller changes from shared to invalid. The other activity which takes place at this fourth step is that the processor P2 finds a CPU write message, so it places write miss on the bus and changes the state from shared to exclusive, and it writes a value 20 at address A1. the address of A1 with the sharer set is placed, and the value available in the sharer set is the processor P2. This is shown here in detail. Now let us see how the finite state machine controller handles the fifth step, that is, when the processor P2 writes a value 40 to the address A2. The first, where P1 being in exclusive state, P2 write miss at A2 occurs. The controller of A2 is in exclusive state and it places P2 in the sharer set. Furthermore, the third action is that P2 writes back 20 at A1 completes. The directory at A1 is in uncached state. The sharer set becomes empty and value 20 is placed in the memory. So this means that in this situation, the sharer set is a null set. And here the P2 remains in exclusive state and the address is A2 having a value of 40. Now with this much explanation regarding the working of finite state machine controller, let us discuss the performance of multiprocessors. First, we will be talking about the performance of multiprocessors in case of symmetric shared memory architecture. We know that in bus-based multiprocessors using invalidation protocols, several phenomena combine to determine the performance of multiprocessor. Here, the overall cache performance is a combination of the behavior of the uniprocessor, cache miss traffic, and the traffic caused by the communication due to invalidation and subsequent cache miss. Furthermore, changing the processor count, the cache size, and the block size affects these two components of miss rate, that is the cache miss traffic and the traffic caused by communication. The misses arising from interprocessor communication, called the coherence misses, can be from two different sources, and these sources are referred to as the true sharing and false sharing. Let us discuss what do we mean by the true sharing, and then we will talk about the false sharing. Regarding the true sharing, the misses arise from communication of data through cache coherence mechanism are referred to as the true sharing misses. Here, in order to explain this concept of true sharing, the first write by the processor to a shared cache block caused an invalidation to establish ownership of that block. However, when another processor attempts to read the modified word, a miss occurs and the resultant block is transferred to the cache. Both the misses are classified in this case as the true sharing misses because both these misses arise from sharing of data, whereas the false sharing arises from the use of invalidation-based coherence algorithm with a single valid bit per cache block. Let us explain this concept of false sharing. We can say that the false sharing occurs when a block is invalidated and a subsequent reference, that is, the reference just after the first reference, causes a miss. That is, we can say the word being written and the word read are different, and the invalidation does not cause a new value to be communicated, but only causes an extra cache miss. Here, the block is shared, but no word in the block is shared. This actually means that we are having the same block, but the words in the block are different and they cannot be shared. And the miss would not occur if the block size were a single word. Now, in order to further explain the concept of true sharing and false sharing, let us reconsider our previous example and assume that the words A1 and A2 are in the same cache block, which is in the shared state in the caches of P1 and processor P2. Now, in this example, we will try to identify the true sharing miss and false sharing miss for the sequence of events shown here. Here, at the first time slot, the operation is processor 1 performs a write at address A1. Processor 2 at the second time slot performs read at A2. And at the third time slot, the processor 1 performs write A1. In the fourth time slot, processor 2 writes at A2, and in the fifth time slot, the processor 1 reads from A2. Now let us see what happens and how we can identify the sharing. The event 1, which is processor 1 writes at A1, this is a true sharing miss because A1 was read by P2 and it needs to be invalidated from P2. Whereas at the second event, which is the processor 2 reads from address A2, this is an example of false sharing miss since A2 was invalidated by the write of A1 in processor 1, but the value of A1 is not used in processor 2. The third event, which is the processor 1 writes to A1, is another example of false sharing miss because the block containing A1 is marked shared due to read in the processor 2, but processor 2 did not read from A1. The fourth event, which is the processor 2 writes at A2, is again a false sharing miss for the same reason as for the third event. Here, in this case, the block containing A2 is marked shared due to read in P2, that is the event number 2, but P2 did not write to address A2. Whereas the fifth event, that is the processor 1 reads from A2, is an example of true sharing miss because here the value being read by the processor 2 was written by processor 2 in event 4. Therefore, it is an example of true sharing miss. Now, with this much discussion about the performance of centralized shared memory architecture, let us talk about the performance of distributed shared memory architecture. The performance of directory-based multiprocessors depend on many of the same factors such as the processor count, the cache size, and the block size. These are the same factors that influence the performance of the bus-based or centralized shared memory architecture. However, in case of distributed shared memory architecture, there are some other factors in addition to these factors, and here the location of requested data item, which depends on both the initial allocation and sharing pattern, also influence the performance of distributed shared memory architecture. The distribution of memory requests between local memory and remote memory is key to the performance of distributed shared memory architecture. This is because it affects both the consumption of global bandwidth and the latency seen by the request. We can visualize this with the help of these graphs shown here. Here, let us first of all consider the graph for cache miss, which is separated into local and remote request, and here we take into consideration different types of graphs. So first of all, let us consider the graph for data miss rate versus the processor count. This graph has been obtained by using the benchmarks such as FFT, ALU, Brains, and Ocean. These graphs show that the miss rate is not affected much by the changes in processor count. However, we can see only in case of benchmark Ocean where the miss rate rises at 64 processors. Also note that this rise is the result of increase in the local misses, which is due to the mapping conflict, and increase in the remote misses resulting from coherence misses. Now let us have a look onto the graph showing the data miss rate for different cache sizes. Here, this graph is also obtained using the same benchmarks as we considered earlier, and this graph shows that the miss rate decreases as the cache size increases. Here, note that there is a steady decrease in the local miss rate, while the decline in the remote miss rate depends on the coherence misses. In all these cases shown here, the decrease in the local miss rate is larger than the decrease in the remote miss rate. And now, finally, let us have a look onto the graph showing the data miss rate vis-a-vis the block size. This graph is also obtained from the same 4 benchmarks which we have discussed earlier, and these graphs show that the miss rate decreases as the block size increases. Now, with this much discussion on to the performance of multiprocessors for centralized and for distributed shared memory architectures, let us have a discussion on to a very useful topic, that is the synchronization. Why we need synchronization? The concept of synchronization becomes important because while using multiprocessor architectures, we need to know when it is safe for different processors to use the shared data. This means that when it is important that different processors are to use the shared data, then we must have some mechanism to establish synchronization in the process. The synchronization mechanisms are built with the user-level software routines. These routines rely on the hardware supplied synchronization instructions. For small microprocessors, uninterruptible instructions are used to fetch and update memory, and this operation, which is used to fetch as well as update the memory at the same time, that is, read from the memory and write into the memory at the same time, this type of operation is referred to as the atomic operation. Now, for the large-scale multiprocessors, synchronization can be a bottleneck. However, several techniques have been proposed so far to reduce the contention and latency of synchronization. Now today, we will examine the hardware primitives which can be used to implement synchronization and then construct some synchronization routines using these primitives. So let us first of all discuss the hardware primitives. While talking about the hardware primitives, we can say that the basic requirement to implement synchronization in a multiprocessor is the set of hardware primitives with the ability to atomically read and modify a memory location. That is, read and modify are performed in one step. It is not divided into number of steps. One typical operation that interchanges a value in a register for a value in a memory atomically is referred to as the atomic exchange. However, there are number of other atomic primitives that can be used to implement synchronization. The key property of these atomic primitive is that they read and update the memory value atomically. That is, without subdividing this into number of steps. In addition to the atomic exchange, the other operations used in many old multiprocessors are the test and set and fetch and increment. Now let us understand the concept of atomic operation and its working with the help of an example. So for this matter, let us consider the atomic exchange operation and to see how we can use this primitive to build synchronization. Let us assume that we want to build a simple lock, and this simple lock is represented such that a value equal to 0 indicates that the lock is free, or the value 1 indicates that the lock is unavailable. To implement synchronization, a processor tries to set the lock by exchange of 1. The value 1 is in the register, and this value is exchanged with the memory address corresponding to the lock. The value returned from the exchange instruction is 1 if some other processor had already claimed access. That is, what do we mean by the lock is unavailable? Otherwise, this value returned is 0. That is, the synchronization is locked and unavailable if some other processor had already claimed access. Otherwise, the value is equal to 0. Now, in this latter case, where the value returned is 0, the value is changed to 1 to prevent any competing exchange from also retrieving the value 0. Now let us consider an example of two processors trying to exchange simultaneously. This race is broken when one of the processor exchange first and it returns a value 0, and the second processor returns a value 1 when it does not exchange. The other atomic instructions, that is the test and set, it tests a value and sets it if the value passes the test. Similarly, fetch and increment instruction is one, which returns the value of a memory location and atomically increments it. However, once again, note that in all these atomic operations, the key factor is that the operation is indivisible. Now, implementing a single atomic instruction in hardware is complex and is hard to have read and write in one instruction. Therefore, the recent microprocessors use pair of instructions. This pair of instruction is having the instructions load linked and store conditional. Here, the second instruction, that is store conditional, returns a value from which it can be deduced that if the instructions were executed as atomic or not. Note that the load link instruction returns the initial value, whereas the store condition instruction returns 1 if it succeeds. That is, no other store to same memory location takes place by the preceding loads, and otherwise its value is equal to 0. Now these instructions are normally used in a sequence if the contents of the memory location specified by the load link are changed before the store conditional to the same address occurs, then we can say that the store conditional fails. With this much discussion onto the uninterruptible instructions to achieve synchronization, we conclude our discussion onto the synchronization of parallel processing architectures, both for distributed and centralized shared memory. Now, to conclude our discussion onto the parallel processing, we have studied the parallel processing architecture as the collection of elements that cooperate and communicate to solve larger problems faster. Here we have noticed that the multiple instruction, multiple data stream architecture can be implemented either as a centralized shared memory architecture or as a distributed shared memory architecture. As a centralized shared memory architecture, it maintains the single centralized memory with uniform access time, while in the distributed memory architecture, which has got non-uniform memory architecture, it can achieve greater scalability. Now, with this much discussion onto the parallel processing, we stop here, and from next time we will take up a new topic. Till then, Allah Hafiz.